Continuing on with the notes on language, last time where we left off, we were talking about grammar and the organization of language, and also then the production of language. A little bit about how maybe Brokaw's area is involved in the organization and production of language. But we wrapped that up by talking about the physical act of production and how the different speech sounds have to be produced by the vocal tract. And one of the things that I kind of talked about a couple of different times was the idea of co-articulation, right? So what happens is that when we pronounce words, the usual idea is that there is a fundamental unit of language. It's a common theme in a lot of psych research is to try to take something that's pretty complex. Human language is a very complex phenomenon, and explain it by reducing it down to simpler concepts. And so the idea of a simpler concept for language would be some kind of basic unit of language, and that unit is usually thought to be the phoneme. And the idea is that when it comes to production, that what we are doing is we are uttering a sequence of phonemes. So when I say the word cat, I am producing the sounds k, a, t. Those are the phonemes, the constituent sounds, right? It's not the letters necessarily. Obviously, we can use letters to represent sounds and spell out words, but at a psychological level, the idea is that what is being organized is the sequence of sounds. But again, though, as noted, when we say a word like cat, we don't say the phonemes individually, right? Because then it would sound like ka-ta, and that's weird. So nobody talks like that, I should hope. So we blend them together, and this blending process is called co-articulation. That means that as I am making the ka sound, I am also preparing to then make the a sound that follows it. And then as I make the ah sound, I'm also preparing to make the ta sound. But another way to think about this is that the way that I pronounce the ah is influenced by the sound that preceded it, which is the ka, and is also influenced by the sound that comes after, which is the ta sound. And likewise, the way in which I pronounce the ta is influenced by the preceding ah. So that would suggest, for example, that the way I pronounce the ta in a word like cat might be a little bit different than in a word like caught, right? So even though it's the same t sound in isolation, the change in the vowel from a to a, cat, caught, changes how I actually make the t sound with my vocal tract. Also, the k sound at the beginning is also altered, right? So the way I pronounce the k in cat might be just very, very subtly different than the way I pronounce the k in caught, right? And to take it one step further, if I have the word cat and bat, now we have the same a vowel in the phoneme there in the middle, but it changes again because now the preceding consonant sound is going to be different. So this is what co-articulation means, is that the act of articulating phonemes is not done in isolation, right? They blend together so that each phoneme is influenced both by the preceding sound and also it's the succeeding sound, right? Now, I want to revisit here on this slide the question of whether the phoneme is really the appropriate so-called unit of speech. That's the usual idea, of course. But this raises another question, which is when it comes to not just producing language, which we covered in the previous video, but now perceiving language, right? We hear other people speaking, and we get a bunch of sound coming into our ears, right? It's a perceptual task at this point. And we have to ask, what is the thing that my ears are hearing here? And it's a weird way to put it, but when we think about vision, we usually don't think about what is the object of perception as being a very difficult thing to do. If I hold up any object like my pen here, it's easy enough for me to say, what is the object of my perception? It's the pen, of course, right? But what about language, right? What is it that we're actually hearing? We normally think that I'm hearing words, right? That I hear somebody say a word like cat, so that's the thing that I report having heard. Now, of course, it could be something a little more complex than that. I didn't list it on the slide, but if you remember when we talked about discourse in the previous video about how language is about taking an idea and converting it into some kind of sound that I can then use to communicate that idea to another person, so that ultimately when the person hears my words, they're actually getting the ideas that I want them to have. Then maybe that idea inside the mind of another person is the true object of perception. But that sounds a little bit odd, so maybe we won't go down that path too much here. But it's worth asking, though, whether or not individual words really represent the true object of perception, or whether we want to reduce it down to something smaller. So we have options here: morphemes, phonemes, and phonetic gestures. So what is a morpheme? A morpheme is something essentially it's basically, I think, let's call it a syllable, right? That's maybe the best way to think of it here. So, for example, let's look at the word speech, which is right at the top of the screen, right? That essentially is a word, but it is also one morpheme, but it has many phonemes, right? Because it has the s sound at the beginning, and then it's followed by the p. And so again, the way the S is pronounced is influenced by that p. The sp sound is different than the sh sound, right? So you got a little bit of a phonemic thing going on, and then you have the E and then the ch. So four phonemes, right? S, p, e, ch. And so in that case, is it the word? Is it the morpheme? Is it the phoneme? Let's come up with a better example for what is a morpheme. Let's look at the word morpheme itself. We have the root morph, right? What does that mean? It means shape and form. And eem here refers to kind of a message or a communicative signal. And then there's the S at the end. If we pluralize morphemes, that becomes an indicator of a plural, but that is in fact a morpheme, to add the S, right? To if it's singular morpheme, by adding the S to make it morphemes, I have changed the shape and form of the word, so the S itself becomes a morpheme, right? And so we can see how morphemes are important for meaning here, because the root word or a suffix or a prefix, those are all the ways in which we change the shape and forms of words, and hence their morph, right? The phonemes, though, are reduced down to constituent sounds. Now, we don't normally think of phonemes as carrying any meaning, because the word cha, the phoneme cha, by itself doesn't contain meaning. But it is meaningful to the extent that if I change a phoneme, I would change the meaning of a word. That's one of the key definitions of a phoneme. So, for example, going back to our cat, bat distinction, or even chat, since I used the ch sound a second ago, those sounds k, b, ch by themselves don't carry meaning, but they are meaningful to the extent that if I change the k in cat to b like bat, it's a completely different word now, right? And likewise, if I change it to ch like chat, one more time, it is a completely different word. So phonemes are, in fact, very directly relevant to meaning. And this is how we define a phoneme, as opposed to any other kind of sound that I might make. Like I could possibly, it's kind of hard to imagine an example here, but if I were to be speaking and I were to trip over my words and make some kind of a non-speech sound in the middle of a word, or if I coughed or sneezed or belched or something in the middle of a word, those are not phonemes. They are not speech sounds. And so even if that one of those sounds occurs in the middle of speaking, it wouldn't alter the meaning of my language as far as any listener is concerned, because none of those sounds contribute any meaningfulness to the language, right? So that would all just get ignored. So that's one of the key themes here, is that a lot of the perceptual research focuses on phonemes as being the real target of the auditory perception of spoken language, and that the ear is trying to decode the presence or absence of specific phonemes. So what that would imply here for hearing the word cat is that I, as a speaker, am trying to assemble those phonemes in order, ka, ta, but then I blend them together and co-articulate to make the word cat. A listener hears that word and their auditory system has to take it and then decompose it back down into its constituent phoneme, so that when the sound cat is heard, their auditory system is able to say, That was a word that is made of the sounds k, a, t. So I'm going to look up, like I'm looking up maybe in a table or in a book, what word has those phonemes k, a, t, and then I realize, oh, it's that word that is referring to this animal, right, that we keep as pets, and that's how speech perception is somewhat said to work, right? Is that we identify what the phonemes were, and that's an auditory perceptual process. And then once we have identified the phonemes, we just do some sort of a lookup and a list and figure out which word it is based on the phonemes that are present. And then we access word meaning after that. So the way the rest of this whole set of notes is going to go is that we need to focus on the auditory side of things, about how the auditory system is even capable of decoding the speech signal to figure out which phonemes are present. And then once that task is done, it needs to recognize the word and then access word meaning. And this is a whole process referred to as spoken word recognition. And there's a whole bunch of different models and theories as to how that actually works. And I'll put that probably into yet another video because there's enough to say about speech perception before we get there. So last one here, phonetic gestures. What's that about? One thing to say about auditory perception is, let me do an example here. I'm going to knock on my desk, right? If you heard that, I think it probably comes through in the audio just fine. I'll move the microphone around. You heard sounds, of course, but if I were to ask you what it is that you heard, you're not going to say, I heard sounds. You're going to say that you heard somebody knocking, sounded like knocking on a desk, maybe even, or something made out of wood or fake wood or whatever this is. And so in a situation like that, what we are really doing is we are identifying the source of the sound, right? The actual sound producing event. It's like when you're listening to music and you're listening and you say, I hear a song, but then you also say, but yes, I also hear the fact that it's guitars and bass and piano and drums and a singer and so forth. And so I'm hearing the actual instruments, and therefore I am, again, hearing the sound producing event, the thing that makes the sound. And so that would suggest then that if we take that kind of thinking to language, spoken language, then what I'm hearing are the movements of the other person's vocal tract, the speaker's vocal tract, all of that stuff about the bilabial and fricative stops and sibilants and the so on and so forth, right? All of that stuff are the phonetic gestures. And so those could be the actual targets of perception, if you will, but not a popular idea. We're going to keep with the phonemes for now. But there's a challenge, right? The challenge is co-articulation. So let's talk about that. Let's come to this slide here. So I have a definition here of phonemes. We need to talk about co-articulation. So here the example is bat, right? And I'm using these forward slashes around the letters to indicate here that we're talking about sounds, not the letters B-A-T, but the sounds B-A-T. And as I noted before, if we change the phoneme, we change the meaning. So if the B becomes a K sound, it becomes cat. So we're going to keep with this idea that we are going to treat these as the essential building blocks of language. Another piece of evidence, by the way, that supports this claim is to look at infant sensitivity to language. One of the very curious findings in infant research is that infants, newborns especially, right, 1 month olds, are really, really good at recognizing speech sounds and distinguishing between different speech sounds. So as it turns out, there's over 100 different sounds that can be possibly used as phonemic sounds in a language. And languages around the world will be different in terms of which phonemes they actually use, so that most of them will end up usually with just 30 or 40 phonemes within their entire phonetic system. But there's situations where there's kind of like minimal overlap, right? There can be some languages that use a bunch of phonemes that are not really present in other languages. So it just depends sort of things on geographic origin and linguistic similarity and things like that. But what we see here is that when we look at newborns, if we do a speech discrimination task, how do we do that in newborns, right? We can't ask them if they recognize a sound, right? But what we can do is we can measure their ability to adapt to a repetitive perceptual stimulus. This is called a habituation technique. And what happens is that if you play speech sounds to 1 month old infants, at first they are very, very interested in these kinds of stimuli, and they will show a high amount of arousal in response to that. But if you repeat the exact same speech sound over and over and over again, then they eventually get habituated, aka bored with it. And so the arousal will drop off. And we can measure arousal in a few different ways in infants, but a very popular way in this kind of research is to measure how fast they suck on a pacifier, of all things. And so what you can do here is you can make a specially outfitted pacifier that has a sensor that detects how fast they suck on it, and you run a wire to a computer, to a data acquisition unit, and then you can just track that. So you can show that initial arousal when you start playing the speech sound, and then you can track their boredom as they slow down. And then once they have sort of leveled off and they're fully habituated and bored with that repetitive sound, let's switch it. So let's say it's a sound like ba, ba, ba. Then again, they're going to get bored after a couple of minutes. So if we switch it from ba to pa, now our question is has the child noticed this difference? Did they actually hear the difference between ba and pa? Well, if we see what is called dishabituation, that means that now they're showing new arousal right at the time of that switch from ba to pa. That would suggest that they heard that difference, and now they're newly interested because it's a new sound, right? So we can see that if we do this research on 1 month olds, they will show dishabituation responses to all of the 100 and plus phonemes that are potentially used in human language. But then something happens in our first year of life, which is that we're likely going to be exposed typically to just one language. Maybe in some cases, a child is growing up in a bilingual household or even a trilingual household, but the idea is that there's going to be a pretty limited amount of language exposure to either one, two languages very typically in that first year of life. And then if we repeat this experiment, but we do it with 10 month olds, what you're going to see is that they no longer will dishabituate to all of those other sounds that are not part of the languages that they have been exposed to. They will only, so what's happening is that they seem to maintain their sensitivity to the phonemic differences of the languages they've been exposed to, but they have lost the ability to really recognize and process the phonemes of those other languages, right? And even though they had this when they were 1 month old, they've lost it, right? This can be explained by some synaptic changes in the brain that are kept active as a function of experience, and the rest get pruned away. We don't need to worry too much over the neuroscience of the whole thing. But the idea is that this does kind of reinforce the idea that phonemes seem to be this building block that newborn infants are kind of ready to go to be able to respond and discriminate phonemes, and that some exposure to language kind of sharpens their ability to really key in on the phonemic structure of the languages they've been exposed to. Now, as I mentioned, we have the co-articulation problem. So let me repeat what I said about the co-articulation problem. If a person is going to say the word cat, the way in which they pronounce the k is influenced by the vowel that comes to follow, so that the k in cat or the k in caught will be pronounced in slightly different ways. And therefore, the vowel that follows it is also influenced both by the preceding consonant as well as the one that comes after. So the reason this is an important issue is that this co-articulation business, I've used this term blurring a few times, right? And what that would then suggest is that the boundaries between the consonants gets kind of blurry. Not consonants, phonemes. The boundaries between the phonemes gets very, very blurry. And therefore, when we look at some sort of graphical representation of speech, like I have here, this is a spectrogram, which shows the spectral properties of sound, the frequencies and the intensities of the sound over time. Time is on the x-axis here. The spacing between the peaks and valleys of all these lines here represents the frequencies, and the heights of those peaks represents the amplitude here. And what I have is I have recorded a person, me, saying the word spectrogram on the top, and then another person has recorded the same word spectrogram on the bottom. And one of the things that we might ask is, can I look at these waveforms and actually find the phonemes? There is a little bit of promise here, right? You can look at this and we say that, if you can see where my mouse is pointing, if it comes through on the recording here, there is this very low amplitude burst of noise that occurs just at 0.1 seconds here into the recording. And that would be the s leading into the spectrogram, right? And then there's this great big burst of high intensity noise here. And so what's happening there is that that's during that bilabial p sound where it gets really quiet just as I interrupt the airflow behind the two lips, but then as it's released and we say peck, right? Spectrogram, right? That release of sound is now the vowel that comes after the p, right? So the p, spectrogram here. So we can see that feature very obviously in the diagram here. And then we get to the next consonant where things get quiet again, and we get the O, tro, right? So there's a little lead in to the O, and then it gets quieter again as we do the stop at the G, and then it becomes gram to wrap things up here a little bit. And this last trailing long bit here is the gram, and maybe there's a little hum of the right there, right? So looking at that at the end might say, oh, there's a little section. So if we looked at this and we thought, okay, I can see the phonemes, right? They're right there. Each one of these little transitions is a distinct marker here that would tell me what's going on here. But what would be critical here is that it's not just the fact that it's one person who says the word spectrogram, but if another person says the word spectrogram, I should be able to recognize that word, which means my ear can detect the presence of the same phonemes and the same patterns when it comes from person A's voice versus person B's voice, right? So here's person B at the bottom who's saying spectrogram. And what we're seeing is that we're seeing a similar global pattern, right? There is that initial burst of noise, but it's a little bit different. It's a little bit louder. And then the qualities of the pectro part here is also just a little bit different, but it's there. But notice it fades away very much faster, right? So the way it fades out is a little different for speaker number one versus speaker number two. And then the delay before we get to the next vowel is also lasting a little bit longer, and also the transition of the tra into the o looks very different here in these lead-ins. And then we transition into the gram, and here in the one on the top, the gram kind of fades away very, very steadily. If we follow the line of those peaks down from the top down to the M humming at the end. But for our second speaker, that is really not present at all. It's a much more irregular kind of decay of the sound. And there's no clear, distinct humming of the M at the end here either. So the presence of that M is not even really there. So what I'm kind of suggesting here is that not only do we talk about the co-articulation issue, that the way in which the sounds get produced depend on the preceding and succeeding sounds, but from person to person, the pronunciations will look a little bit different. And when we try to graph and look for patterns in these graphical representations of the sound wave, the patterns don't really look exactly the same. And that makes it harder to say then, okay, if the ear's job is to take this sound and analyze it to figure out which components of these sound waveforms specify the phonemes that are present. The challenge here is that it's hard to really do this. And I say it's hard to do it, but what I'm saying is that decades of research has gone into trying to analyze speech waveforms, and researchers have never really successfully managed to decode these things to say that the presence of this kind of pattern will indicate the presence of a specific phoneme, right? To explain exactly what it is the ears are keying in on here. To further dive into this a little bit, let's illustrate co-articulation. So here I have a recording of myself saying the word spectrogram, as we previously saw. But now I also have a recording of the milligram. And so the milli part is a lot harder to see at the bottom. But what we see is that that alters the transition into the gram component, right? So we have the same morpheme at the end, gram, but now the two grams look a little bit different from each other because of the different sounds that came before. Um, Now here is a recording of saying tram versus gram. So again, we changed the starting t sound, and we've really caused a transformation, not just at the beginning, but even that lead into the ram part of it just is a bit different, right? So things just change again from once we start introducing small changes to the consonants here. Um, Now, here I tried something that's just a little bit more for fun than anything. I guess you could say it's that. So I recorded myself saying right? And those are the phonemes of ram. And then I have kind of taken a little bit of each one of those and I stuck them together at the bottom to create a sequence of sounds so that maybe if we blended all of that together, it would look like the previous waveform for the word ram. And it doesn't at all look the same. And I can't play this back for you, but if we tried to play it back for you, we might ask, could it sound like ram? And no, it doesn't. It just it sounds kind of like right? It doesn't sound anything at all like the word. So grabbing bits and pieces of these sound waves and just sticking them together like that, it doesn't really replicate language, right? The blending is more natural when it comes to co-articulation. So that means the challenge, of course, for auditory perception of language is how does the ear decode that signal and recognize the phonemes that are present? The answer is we don't have a good answer for that, right? It's a very, very hard scientific problem. The so-called Hackett's Easter egg analogy is described here, right? So what's happening is that what Hackett is suggesting here is he's given us this analogy where you're going to say, okay, what if we imagine a situation where I have a machine where I'm going to take Easter eggs, right? Eggs that are painted with nice decorative patterns, and I'm going to put them onto a big conveyor belt, and I'm going to send them down the line on this conveyor belt one at a time. And each Easter egg is unique and different from all the others. But as I send them down this conveyor belt, there's this big machine that comes down and smashes them. It just breaks them and crushes them into a bunch of pieces. And then another machine kind of swirls them around and mixes them all up so that at the end of the line, you have a bunch of broken Easter eggs that are kind of still roughly where they were, but they kind of got mixed up with each other a little bit. And now somebody's job at the end of the line is to somehow put Humpty Dumpty back together again, right? To reassemble all these broken parts back into the original Easter eggs to figure out what they were and what was the design that was on that egg. And this seems to be, of course, an impossible task. It's the lesson of the nursery rhyme, right? That Humpty Dumpty couldn't be put back together again, right? So, in that situation, this is, he's using this as an analogy for what happens to the phonemes, right? That when I am sequencing the phonemes in the speech production centers of the brain, it's sort of like the nice, perfect Easter eggs getting all lined up in sequence. But then in the act of articulating them and co-articulating them, it's sort of like the machine that smashes them all up and mixes them all together. And then the ear of the listener, that's the person who has to put it all back together again and restore the original phonemes. And again, it seems like an impossible job here. So this could lead to a couple of different conclusions here. One is that maybe we need to have a different analytical approach that looks for different kinds of patterns in the sound wave. And certainly there's a lot of work on that. I don't necessarily think we need to go down that particular rabbit hole, but nevertheless, that's one pathway, is just different analyses of the speech waveforms to find patterns that really are consistently present when specific phonemes are present. Another approach is to redefine how we are looking at language here and maybe reconsider whether the phoneme is the appropriate target here, and maybe it's something else, morphemes, words, and gestures, right? On the idea of that phonetic gesture, as I have mentioned previously, is some evidence for that, right? So we have a theory called the motor theory of speech perception that argues that what's happening is that when we hear another person speaking, that yes, we are hearing their phonetic gestures, we are really attending more to the movements of their vocal tract. But the way that this works is that the signal actually activates some of the same motor areas in my brain that would be active if I was producing those sounds myself. This is maybe a little reminiscent of some ideas. If you've heard of mirror neurons before, the folks involved in the motor theory of speech perception, I don't think are directly invoking mirror neurons, but nevertheless, the kind of idea here that recognition occurs by kind of recognizing the social recognition, at least, is occurring because I'm recognizing the same movements that I would perform if I was making those same sounds, right? And that might help us then recognize the movement of the speaker's vocal tract. One pretty interesting piece of evidence for this is something called the McGurk effect here. So let's see if playing this video inside the video works here. If this doesn't work and come through in my recording, you can just search on YouTube for the McGurk effect and you can see it for yourself. But what's happening here is that we're going to, you see that I think gives us an instruction to keep our eyes closed.
It's called the McGurk effect. Ba, 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 ba. What do you think he's saying? If you think he's saying da, 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 you are in the grand majority. But now, close your eyes and listen instead of watching. Ba, 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 ba. The voice is saying ba, ba, ba. Now, let's replay it without the sound. Yes, it's true. His lips are saying ga, ga, ga.
Okay, I'll stop it there. So what's going on here? So as you can see, the recording, the actual sound that is coming through the speakers is the ba sound. But the speaker's vocal tract is actually, as we observe it, if we look at it, it is a ga sound, right? But that's when we watch it with so if you keep your eyes closed, you're just going to hear the ba, right? But when you watch the guy moving his lips and you're hearing that ba, it gets rendered as a da. And the explanation for this is that the perception of the sound is simultaneously influenced both by the sound waves that are coming into your ears, but also your visual perception of the speaker's vocal tract and the movements of their vocal tract. And what happens here is something of a blending or averaging process because the ba is produced at the front of the mouth, the ga is produced at the back of the mouth. That's a velar stop. And so what sits halfway between the lips and the velum is the alveolar ridge, and that's the da sound. And so in this situation, we would explain the perception of da as the so-called McGurk effect illusion as the blending of the auditory ba with the visual ga, and they average each other out, and that results in the da. And taken as a whole, this would suggest then that yes, the fact that visual perception of the movements of a person's vocal tract are kind of a pretty important part of auditory perception. Anyone who maybe struggles to hear, right, if you have some hearing problems or if you're just in a noisy environment, it usually helps to try to look at another person when they're talking to you so you can read their lips at the same time. That helps you make out what they're saying. It's consistent with this idea that what we are really gaining here is information more focused on those phonetic gestures rather than just on pure phonemes that are coming through this auditory waveform here. One last thing to say about one problem with the phoneme theory. I have this note here about it kind of ignoring speaker-specific characteristics. And so this didn't come through super well in my waveforms where I had two different speakers saying the same word. There was little hints of it in there. But the idea is that people, speak differently. They have different accents. They have different pitches. They speak with different intonation patterns called prosody. And what's important about prosody is that these intonation patterns that can indicate one's emotional state or whether you're asking a question or making a statement or issuing a command, these are considered to be non-phonemic, right? They don't contain phonemes, but they do carry information and they do carry meaning. And so this idea of there being non-phonemic sources of information in language is pretty important. It's a significant part of language perception that any theory that tries to take a reductionist view by just explaining it all away in terms of phonemes certainly is not going to account for the whole big picture. So this would all kind of be taken together to suggest that we need to go beyond the phonemes to look for the real information of language. That's not to suggest that we have an answer to that, right? This note at the bottom about the waveform not being an adequate way to graphically capture the acoustic patterns and analyze it. That's what I was suggesting a couple of minutes ago about there being different analytical approaches that just can reanalyze the sound waves in different ways. But again, with that rabbit hole, we're not going to go in that down that one. So we will shift over next to whoops. Ba. Okay. I'm trying to go to the next slide here if it'll let me. Whoops. What was that?
Brains read.
There we go. Here's one example of that, though, before we finish it up, right? So this is just a different way of graphing the sound. What we're going to do is we still have time on the x-axis, but now we have frequency on the y-axis instead of amplitude. And what we see is that there are these concentrated areas of energy here called formants, right? These dark bands. And what we see is that there are typically three formants within the speech sounds. And so this is a recording of someone saying, "I can see you." Now, the consonants are not clearly specified here. The ka, the s, those are in there, but it's just a kind of a mess of noise. But the idea is that these three formants for the I, a, e, oo, and I can see you. Nice, all the vowels are in there, right? Then what we're going to get here is different patterns of formants here that could uniquely correspond to the different vowels. And that sounds very promising, except for the fact that what I said before remains true, that in a word like can, where we see the three formants that correspond to the a in can, again, if I switch it to the word cat, the formants will suddenly look a little different. So they won't be exactly the same. And then, so it's going to be harder for us to say that, yes, that particular configuration of those three bands of energy is not always there and doesn't always look exactly the same whenever the ah sound is present. So it's a nice, promising line of research, but it doesn't necessarily completely tell the whole story. But one area where it is somewhat promising here is in the generation of synthetic speech sounds. So if you've ever heard synthetic speech, it's actually really good now, right? We got a lot of AI stuff that generates artificial language, both not just textual, but also it can generate artificial synthetic speech. But the way it was originally done was a little different. And so if you've ever heard, say, Professor Hawking speak, right, his early speech synthesizers were not so great and not necessarily very human sounding. It originates with this kind of stuff. So what the researchers did is that they could essentially program a computer to make this formant sounds, right? And one of the things they found is that if you play just a single formant, it doesn't sound like language at all. It actually sounds kind of like a whistle. But if you play two formants, it sounds a little bit more like a phoneme. And if you play three formants, it sounds even more like a phoneme. But the argument here is that a minimum of two formants are necessary to create a speech-like sound. So the researchers wanted to find out, well, what can we look for patterns here that is where it's treated as a specific kind of sound. So on the top, we have the synthetic data. So these are the actual synthetically generated, artificially generated formants that are played back through a computer. And so we have 14 such stimuli. And we see that one of the key manipulations is this sort of tail that leads into the formant at the beginning of the sound. And so for stimulus one, it's kind of hanging down on the top formant, very, very pronounced. And then they're kind of trimming and leveling that tail off as we go towards stimulus 4, 5, 6. It kind of flattens out there. And it stays flat as we go through 9 and 10. It starts to kind of flip up, right? And then that continues more pronounced as we go through all the way to stimulus 14. So technically what we have here are 14 different sounds. But when we ask people to identify them and to report what they hear, the answer is not 14 different things. The answer turns out to be 3 different things. And that's what the identification data at the bottom are showing here, is that the first 3 stimuli are very, very reliably, 90+% are reported as being a ba sound. Once we get to stimulus 4 and 5, there's a little bit of confusion, a little ambiguity, but nevertheless, once we get to stimulus, is that 5 or 6 at this point, it's da, right? And it stays pretty steady at da all the way until we get to stimulus, 9 or 10. And then there's some ambiguity, and then it becomes a much more consistent ga perception. So this is called categorical perception, because what's happening is that we're taking 14 stimuli that are just varying continuously, but perception doesn't work by hearing continuous variations. Perception likes to group things into categories, and that's exactly what's happening here. This shows then that maybe the idea is that even though there are subtle variations in pronunciation as a result of co-articulation and speaker-specific characteristics, that maybe there's enough robustness in the auditory perception experiment or perceptual system that it can handle that kind of variation and still put things together into the same category and say that those are still all ba sounds or da sounds or gus sounds, right? So this would actually be consistent with the phonemic approach to things, but it would just show that we need a different kind of analytical approach to look for these different kinds of patterns, the formants, and understand them in those terms rather than looking at the waveforms. But having said that, well, of course, one of the things we see is that even when you generate computerized speech using synthetic formants, even if you throw in a third format to make it sound a little bit better, it never really truly sounds like natural language, and it's a little bit hard to understand. So that's why a lot of more modern AI-generated synthetic speech sounds a lot better because it uses a different kind of technique. Okay, so following up on that, as I mentioned at the beginning of the video, we have to also cover these models of word recognition. So once we have tackled the whole issue of perception, decomposing the sound into the phonemes, now we have to turn those phonemes into words and access the appropriate word meaning. This is a challenge when it comes to the fact that sometimes words have multiple meanings, and now we need to think about the importance of, say, context and things of this nature. Now, this is a whole deep dive, so I'm going to make this a whole separate video, but that's where we're headed next. So I will see you then in the next video.